Hello everyone and welcome to the OneClass channel. My name is Donna Riel and I'm a recent master's graduate in the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you had any problems with homework or tutoring, then check out the links in the description below. So now we're just going to get started on the first set of questions. Okay, so question number 1. If you put 120 volts of electricity through a pickle, the pickle will smoke and start glowing an orange-yellow color. The light is emitted because the sodium ions in the pickle become excited, and then they return to the ground state, resulting in light emission. Question 1a. The wavelength of this emitted light is 589 nanometers. Calculate its frequency. B. What is the energy of 0.1 mole of these photons? C. Calculate the energy gap between the excited and ground states for the sodium ion. And then for D, if you soak the pickle for a long time in a different salt solution, such as strontium chloride, would you still observe 589 nanometer light emission? Why or why not? Okay, so that's kind of a cool question. So let's try to answer part A. The wavelength of this emitted light is 589 nanometers. So let me just write that down. And then from here, I'm going to convert from nanometers to meters, and I'll explain why in a bit. So it becomes 5.89 times 10 to the negative 7 meters. And the reason I did that is because I'm going to use this equation to calculate for frequency. C equals frequency times wavelength, where C is the speed of light. So let me just rewrite this equation that we're looking for frequency. And then the reason I wanted to convert from nanometers to meters is because the speed of light constant is in meters per second. So if I plug all my values in, the speed of light is 3 times 10 to the 8 meters per second. And then our wavelength is the 5.89 times 10 to the negative 7 meters. And then you'll notice that the units for meters cancels out. And then we're left with a final frequency value of 5.09 times 10 to the 14 1 over S, which is also the same thing as hertz. Okay, so that's part A. Part B asks, what is the energy of 0.1 mole of these photons? So for this question, to calculate for energy, it's going to be Planck's constant times F, which is what we calculated in the other question. But if you wanted to see what this equation looked like if we didn't calculate for it, it would be energy equals Planck's constant times the speed of light over wavelength. But in our case, we're lucky since we know the value for frequency. Now we just have to plug in Planck's constant, which is 6.626 times 10 to the negative 34, and its units are in joules times seconds. And then once we plug in the frequency, which is 5.09 times 10 to the 14, 1 over seconds, you'll notice that our seconds cancel out. And then we are left with an energy value of 20,323 joules. Or we can convert this to kilojoules just to make it a little clearer. 20.3 kilojoules. And then this is per photon. The question asks, what is the energy of 0.1 mole of these photons? So all we have to do is multiply this value first by Avogadro's number and then by the number of moles. So let me just write this down. Energy of 0.1 mole is equal to, oh, sorry. I skipped ahead a little bit. Let me just rewrite the actual answer for this. Okay, so multiplying Planck's constant by frequency will actually give you 3.37 times 10 to the negative 19. And then this is in joules per photon. So let me write that down here. We have our 3.37 times 10 to the negative 19 joules per photon. And then I'm going to multiply by Avogadro's number. So every time you have like moles involved and they want to find out how many particles, or if you have the number of particles or photons and you want to convert to moles, you know you want to use Avogadro's number. And the units for this is photons per mole. And then I'm going to multiply by 0.1 moles. Then you notice the photons cancel out, and then the moles cancel out. And then you get 20,323 joules, or 20.3 kilojoules. And then this is the answer for part B. Okay, now for C. Calculate the energy gap between the excited and ground states for the sodium ion. So we actually this is actually our answer that we got here, which is the 3.37 times 10 to the negative 19 joules per photon. So this is the energy gap between the excited state and the ground states for the sodium ion. And then part D asks, if you soak the pickle for a long time in a different salt solution, such as strontium chloride, would you still observe 589 nanometers light emission? Why or why not? So the answer for this is no, you would not, and that is because the energy gap between the ground state and the excited state of strontium. Will be different. Okay, so each element will have like a different energy gap since they all have different numbers of photons. And then let's check out the answer from our junior tutor. They said the speed of light equals frequency times wavelength, and then they calculated frequency to be 5.09 times 10 to the 14 hertz. B, they also got 20.3 kilojoules. For C, they had the 3.37 times 10 to the 19 joules per photon. And then they also converted to EV, which I didn't do, but it's still correct. And then no, because the gap between excited and ground states is dependent on the ions available. Sodium has a 509 emission, but strontium does not necessarily have a 589 emission either. The emission spectra is dependent on the nuclear charge of the species. So this solution was well written. It is correct. So solution is correct. Okay, so now we can